No. But my background actually is in chemistry. Okay? You might be like, well, if your background's in chemistry, why are you teaching astronomy? And there is definitely some intersection between chemistry and astronomy. Yes, ma'am. Do I need to go back one more? Oh, thank you. Good call. So we'll get to the atom here in a minute. Before we get to the atom, this is an important slide. What was the little acronym I said if you're trying to remember the colors of the rainbow? What did I say you could do? Roy G. Biver. You would tell me you could do that. Exactly. And so sometimes, there it is, sometimes I'll write it backwards. I'll show you why. Sometimes I go, let me make it this big. I go Roy, R-O-Y, backwards. I put G for green, and I put blue, and then what does the I stand for? Indigo. Pretty color. Don't know. And V stands, of course, for violet. The reason I put it backwards like that, Roy G. Biv backwards, is because then I'm kind of setting up for which one's the, well, it already says here. Above the red, I'm going to put long, what's this symbol for? What's that symbol? Long what? Wavelength. Wavelength, yep. I'll put that above the red, and I'm going to put short wavelength over the violet. Cool. Well, we said that light, okay, this is all of light, okay? This is just light. But light is only one cousin in the series of cousins. What did we say was the shortest wavelength of electromagnetic radiation? Aside from cosmic, then what does it go? Starts letter G? Gamma, exactly. So over here in the short wavelength, I'm going to run out of room. I'm going to put gamma. What comes after gamma? X-rays, starts letter X. X-rays. What comes after X-rays? Ultraviolet. I'll just put UV for ultraviolet if that works for you. So I've gone ahead and put the three cousins that are shorter wavelength, higher energy than visible light. Very good. And I like this, maybe you guys do too. Do you like this little link, the V's and the V's? Okay, the ultraviolet kind of bumps up against the visible violet. Okay, we can't with our eyes see these cousins. Okay, I just think that is so cool. Okay, so what's a little bit longer than, what's the longer wavelength after light? Infrared, very good. So I'll just put IR. I'm going to put heat next to that. Make sure we're all kind of on that same page. I also like that one. Do you see how the R's match up? The red in Roy G. Biv matches up with the infrared. I'm liking that. Okay, so what's a little bit longer than infrared? I get these mixed up. Not quite radio yet. Microwaves, yep. And there's a little bit of overlap. Like that poster I brought on Monday, there's definitely overlap, which kind of confuses me too. So what's a little bit longer than microwaves? Radio. So those are the cousins. And while I'm at it, let's see, how does this work? I'm going to go over, okay, this could be, oops, better pick a different color other than black. Okay, here you see the prism, like Newton did, separating white light into its colors, right? Okay, so we have red over here, and we have violet over here. Roy G. Biv in the rainbow. I think this is right. I don't know if it was Newton or somebody else, but they actually laid a thermometer right here. That's my thermometer, okay? And you can't see it, but that prism was also separating infrared thermal energy. So that thermometer got warm relative to it being outside. Isn't that cool? I mean, just invisible. Anyway, it's me. Okay. So we'll be talking about the cousins and different types of astronomy. Now this is where I thought we were. Now we're back to the don't be scared, my background's in chemistry. But chemistry and astronomy are both physical sciences, so I think it works pretty well, aside from the fact that I just love the stuff, you know. Now we need to talk about atoms a little bit, okay? Because, of course, planets are made up of atoms, okay? So we're going to kind of talk about that. So the things about an atom, and you maybe already kind of know this, is that they kind of have a hard center. We call the source letter N. Nucleus. The hard center's in the nucleus. And then it has, what's that fuzzy thing outside the nucleus? What
Electron
particle is?
cloud.
Yes, electron cloud. Very good, electron cloud. A lot of stuff that we know about stars and I guess planets too has to do with, when I do this, that's my electrons, okay? We actually kind of understand composition due to what the electrons are doing. All right, so the protons are positively charged. The protons and the neutrons make up the nucleus, and the electrons are out here, okay? All right. By the way, the protons are pretty awesome, so are neutrons, but the protons in the center of an atom say what element it is. So I always try to teach in this room, because in this room, what's that called? Periodic table, yeah. I always teach in here, if I can, because there's a periodic table. Periodic tables, of course, have the letters that say what element that, each box is a different element. And if you look, I don't think from here, yes you can. That red number that I can see from here, actually that's the number of protons in the nucleus of an atom of that type of element. It is so awesome. So honestly, as we start to talk about stars, we're going to visit the periodic table. We're going to look at elements a little bit. So if you look at the red number, notice that the red number for hydrogen is 1 proton. The red number for helium, 2 protons. For lithium, 3 protons. And the way that periodic table is organized is you complete a row, then you go on to the next row, then you go on to the next row, and the next row, okay? And it's an increasing number of protons. All right. Speaking of protons, the number of protons in the center of an atom is so important, we call that the atomic number. So the atomic number is just the red number of protons, okay? There's another thing, well, there's all sorts of things. But one of the things we see in outer space is, what's this? The electrons. One of the things that we see in outer space is that electrons sometimes, under certain conditions, can be stripped from an atom. Okay, we call that actually ionization. Okay, if an electron is stripped from an atom, then what kind of charge is an electron? Is it positive or negative? It's negative. Electron's negative, so if it goes away, and it makes it positive, exactly. Okay, so that actually leaves something we call an ion. If it has equal number of protons and electrons, it's what we call neutral. Okay, so electrons can kind of come and go a little bit. So, atomic number is what?
Number of protons.
Number of protons. Atomic number is number of protons. Then there's this other thing that's important in chemistry, and it has to do with looking at the nucleus of an atom. What is in the center with the protons? Neutrons, exactly. So another important thing about an atom is you look in the center and you count protons and neutrons, and we call that the mass number. Okay? Yes?
Okay, I'm just confused. Okay, so electrons in a normal atom are equal to protons.
Right.
So does that mean there's just as many electrons as protons?
Right.
But how, though? Because they're so tiny.
I don't know how to answer that. But I do know that most stuff is neutral. I think of most atoms as being neutral. And so Lindsay was asking up here, so protons, there's the same number of electrons and protons in most atoms, and that's true.
Isn't this how chemistry works?
Yeah, it's very, and we're not going to get into that too much. That's how chemistry works. In a way, stuff sticks together because of what the electrons do between atoms and make what we call compounds. Yep. Okay. This is your crash course in chemistry. Okay, so ions was basically what gets stripped away? An electron. And on Earth, a lot of times, sometimes, actually an electron doesn't get stripped away, an electron gets added. And then actually you have too many electrons, it becomes negatively charged. That's also an ion. But in outer space, a lot of times it's stripping up an electron. Now this other thing starts with an I, it's called an isotope. Okay, so I've got examples of isotopes down here. Have you ever heard of carbon, I think it's carbon-14 dating? Mm-hmm. Okay, carbon-14. Of course, the symbol for carbon is C, okay? And then you see some numbers on the upper left-hand corner. We have carbon-14, carbon-13, and carbon-12. The most normal form of carbon is carbon-12. Now, if you can find carbon on the periodic table, what's that red number for carbon? It is 6. Very good. So that's 6 protons. That number up here, carbon 14, carbon 13, carbon 12, that is the mass number, which is protons, which is 6, plus neutrons, which is, I don't know. So do you guys buy this? That in this case, there are 6 neutrons. In this case, there are 7 neutrons. And in this case, there are 8 neutrons. How do I get that? Well, because the mass number is in the upper left-hand corner. Let me show you how that looks. So here we go. 6 plus 6 is 12. 6 plus 7, 13. 6 plus 8 is 14. In all of those cases, they have 6 protons, but they have an assortment of neutrons. Now, Mother Nature's pretty picky with how it does that, okay? There are some stable nuclei, and then there are some unstable nuclei, okay? So it's not just a willy-nilly thing. But those are 4 different isotopes of carbon.
But aren't electrons like where the magic happens, like why everything happens, I guess?
I'm not talking about electrons now. You're talking about chemistry, and I really...
Oh, okay.
He's asking, are the electrons where the magic happens? Sort of, but the protons give identity, chemical, elemental identity to an atom. So protons are pretty darn important. Electrons are massless, so when it comes to mass and, comes to things like gravity, it's the protons and the neutrons that kind of make that magic happen. Electrons are most important on Earth in chemical bonding. Electrons are very important in astronomy for identifying things. So, isotopes, gotta love them. Okay, what else we got here? So these are 3 isotopes of carbon. What is He the symbol for? Helium, very good. Helium has how many protons in its center? 2, perfect. Hydrogen has how many protons in its center? 1, exactly. So here we're showing hydrogen 1, mass number 1, helium, mass number 4, and carbon, mass number 12. Just 3 different atoms, 3 different elements. But what identifies the element is the number of protons. So down here, this first column right here, you guys told me, so atomic number, you guys told me 1 proton for hydrogen, you guys told me 2 protons for helium, and you guys told me, I don't know if I asked, but 6 protons for carbon. Okay. All right. So we've been talking about on Earth what's important, and actually in outer space, let's see, when am I going to talk about this? Oh my gosh. In outer space, if you leave the Earth and travel to the closest star, and then if you keep traveling and leave our Milky Way galaxy, and you take a bird's eye view, basically, of the universe, we're going to see that most atoms, like 99.5% of the atoms, are all hydrogen atoms, which totally blows my mind. Because if you look around, we definitely count on more than just hydrogen atoms as we live our day-to-day lives. Okay? So most atoms in the universe are hydrogen atoms. In outer space, I just think this is so cool too, we do find molecules. Now, if you're kind of familiar with what a molecule is, basically it's 2 or more atoms of different types of elements that are stuck together. The reason they're stuck together has to do with their electrons that they're either sharing or transferred, probably most likely sharing in outer space. Okay? So, H2O, what element, or excuse me, what compound is that? Water. Exactly. CO2, what compound is that? Carbon dioxide. NaCl? Table salt. NaCl is table salt. These are all compounds. C6H6 is benzene. So, benzene is benzene. Benzene is a carcinogen, and I guess it's really kind of fun. Benzene, actually those 6 carbons do a circle. So we have carbon, 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 carbon. Let's see, how do I read carbon? Do I have 6 there? Not a very good. No, I only have 5. Are you serious? Okay. Carbon, carbon. Oops. 1, 2, 3, 4, 5. Oh my gosh, are you serious? They're going to take back my chemistry degree. Carbon, carbon, carbon. This is the bottom of the hexagon. This is the other side. Final answer. These things that I'm drawing in orange, those are the chemical bonds between the carbon atoms. And then I'm missing my hydrogens, right? So here we go. It's just a really kind of a pretty... this last Christmas, I was talking about this in chemistry, and I tried to find, don't you think that would make a great Christmas wreath? I could not find one. To me, that looks like... Now, one more thing, just so I don't totally take my degree away, is we have alternating single and double bonds. So we'll make that one single, double, single, double, single, double. And all that double bond means is there's extra electrons being shared there. That's one resonance structure of benzene.
So like the carbons would have an extra electron?
So that actually every time you see a dash, there's actually 2 electrons shared. So if we see 2 dashes here, how many electrons are shared? 4. 4 electrons are shared. Yep. But with all that said, I'm going to tell you probably one of the most important molecules in outer space that we're going to talk about, and it's this one. What molecule is that? Carbon monoxide. Yep, carbon monoxide. I just think it's amazing that most of the atoms in outer space are hydrogen, and then the odds of them getting together and making a compound, you're like, are you serious? It's just amazing. In chapter 6, we're going to talk about the formation of our solar system. And, you know, you definitely, in order for our planet to be what it is, you had to have hydrogen and oxygen get together to make H2O. Okay? I just think that's so cool.
Isn't the flash point of hydrogen really low? Or
That I don't know. I'd have to, it sounds right. It sounds right. Yeah, I don't think, it's hard to make liquid hydrogen. So. Okay. Now, okay, so we talked about atoms. Okay, do you guys buy this? All matter is made up of atoms. So there's atoms in the table, atoms everywhere. Okay, atoms in the air. Are there atoms in the air? Yeah. So we need to be able to talk about how energy and matter, energy and atoms interact. Okay. So down there at the bottom is kind of entangled in this slide are the 4 ways that this is what's this? Energy, my radiation, yep. Okay, and this is my matter. We need to talk about how they can interact. And there's 4 things that can happen. For instance, matter can emit light. So if this is my matter, check this out. Does this make sense? It's emitting light. This is my matter emitting light. Okay, matter can emit light. Good with that? We'll talk about a little bit why that happens. What else can happen? Well, matter can absorb light. And we're going to talk about this. So for instance, it's a sunny day. It's summertime. What color of t-shirt do you not wear on a sunny day when the sun, yeah, you do not wear black. And we're going to talk a little bit about colors, why we see colors, okay? But if you see something that's black, this is my fist, okay, this is light, okay, basically the matter absorbs all that light energy, okay? So it can emit it, it can absorb radiation. This third one up here, what can also happen? Well, what happens when you see a window, when you look through a window? It just goes through, okay? Matter can just let energy just pass right through it. And then the last one is reflected or scattered. And I have an example up here. But the last example is really very, very broad. And I'm going to try to convince you of this. But the reason I can see this table right here is because basically light has hit the table, okay, and that table is scattering light in all directions, including my eye. Can you see the table too? Okay, so the light is going that way and this way, and can you see the table? And this way. If I was hovering up here, can I see the table? Okay, so light hits the table and it's scattered in all directions so everybody can see the table. That's the last thing, scattering. So what color of shirt do you wear if it's a sunny day? Not a black, what do you wear? White. Now I'm going to try to convince you, if you see something white, like this, okay? The thing about, if you see something white, basically light is hitting that, and the reason you see it white is Roy G. Biv, what's that? Colors of the rainbow. All colors of the rainbow are basically being scattered back off of that, and this is just so amazing. And our mind kind of puts them all together, makes them a composite color, which is white light. Okay, when you see something black, all the light is absorbed. When you see something white, all the light is reflected. I just think that is so cool. So I've got some, so I kind of said this. If we see an object that's white, all the colors, okay, sorry. If we see something that's being illuminated with white light, okay, only the color, let's see, all colors except the color we see are absorbed. I've got some examples coming up. All right. So I like this figure. So check out this green tree. What's this light here coming in from the left? It's Roy G. Biv. Very good. This is coming from the sun, which is, I'm probably going to go ahead and put Roy G. Biv over that light ray. Perfect. So Roy G. Biv. So that means that tree is absorbing Roy, without the G, Biv. Where's the G going? It's being scattered. Yeah, G is being scattered. G is being scattered. I always have to concentrate on this part of the lecture. Okay? All right, so the guy's inside. Let's look at the chair. Okay? So the chair is being illuminated by Roy G. Biv from the lamp. So I'll put Roy G. Biv from the lamp. Coming from the lamp. Okay, what colors is the chair sucking in? Roy G. Biv. Right. Roy G. Biv. And what color is it scattering back? Just red. That is so cool.
So the light colors absorb out of that, the ones that are the same will be absorbed and scattered, and the other ones will, I'm confused.
Yeah,
You have
so
two
if
of one
it's
kind of-
if it's white, everything comes back.
Yeah.
And if it's black, everything's absorbed. And then there's kind of some variations. So the color you see is the color that's reflected back. And if it's black, there's nothing reflected back.
Is the Roy G. Biv like just the colors?
The Roy G. Biv is just the colors of the rainbow. Yep. It's all colors of visible light. And there's where we kind of get a little bit into, if you get a chance to go to Lowe's, oh my gosh, look at their technology with their light bulbs these days. Because you're like, are you serious? So you can kind of tweak the light bulbs so they're kind of sending out kind of subtle different sort of set of wavelengths. And it kind of things look different under different lights.
So all the colors are there, but only certain colors are what's reflected out of it.
Right.
Okay.
Exactly.
I'm trying to grasp it.
Exactly. And then I've thought about this before. Have you ever done the whole black light thing? So you're like, okay, so that's only one wavelength shining on everything. So that's why if it's not that color, things look black. I know, because there's not that color to, yeah, it hurts my brain. But it is so cool. A lot of things hurt my brain. Okay. Now we need to go back to the atom a little bit. So what's this?
Electrons.
It's my electrons. And the electrons actually, even though the whole atom has kind of, all matter has motion. We talked about that with temperature, didn't we? All matter has motion. Okay, the whole atom's moving. Okay, if it's in its gaseous state, oh my gosh, you cannot stop that atom. But even if it is solid state, like atoms here are kind of moving like this, but the electrons are moving the most. Okay, so anyway. So electrons, okay, they like to be couch potatoes. Like, okay, so let's pick on carbon. So the red number for carbon is 6. That's the number of what? Protons. If it's neutral, how many electrons does carbon have? Also 6. Yep. And what those 6 electrons around a carbon atom like to do is kind of be huddled down in what we call their ground state. Now the thing about electrons is they can, when I go like this, there's a world out there where those electrons can be in what we call an excited energy state. But they like to be ground state. Don't we all? If we can. Okay? So that's kind of what we're talking about when we talk about ground state. So I brought this chair. I hope I don't never done this before. I brought this chair to kind of show you the whole electron thing. So I'm going to take off my shoes. Okay. So as I'm down here, kind of think of I'm an electron, and underneath my feet is the nucleus that I'm associated with. Okay. So, and I heard another teacher do this before, and she was successful. So we'll see how I do. Now, if I get energy from somewhere, actually, I can jump up. Okay. Notice I'm farther from my nucleus. Okay. I'm at an excited energy level. I'm an electron still associated with that nucleus, but I am at a higher energy level. Did it take some energy to do this? Yeah. And I don't know if you buy this, but how does this work? But when I step down, actually, it's not real obvious, but when I step down, I'm going to release energy. Okay? So this takes energy, okay? And when I step down, I'm going to release energy. All right. Cool. So electrons can jump, okay, between energy levels. Now, this says absorbed or emitted. So which one is this? Is this absorbed or emitted? Is energy absorbed or emitted? Absorbed. Energy is absorbed.
Oh no.
I took energy to do this. Okay? When I step back down, is energy absorbed or emitted? Emitted. Yep. Now, we'll go back to our light bulbs. Actually, I brought this here today.
So why does electron go from state to state?
Why? Okay, this is actually, I don't know how this is going to affect my recording, but this is one of the reasons that electrons can be promoted from their ground state. What is actually, in here is neon gas. Okay, I could turn off this tube and it would just look like a clear tube. There's neon gas in there. So what is actually being supplied between, it's plugged in, that's your hint. What's going from one electrode to another electrode? Electricity. I was talking to my mom about electricity. She's like, well, how does electricity do that to promote electrons? I'm like, I don't know, but it does. So electricity can do this. Okay, so that's what's happening. Electricity is doing this. Okay, now, what color do you see that as? Red, orange, very good. The reason you see it is because of this. That's not an electricity thing. That's the visible part. What happens when I do this is energy absorbed or emitted. Emitted. Energy is emitted as I step down. So it's kind of a continual process. Those cute little neon atoms, and they're minding their own business, take some electricity. The electrons are promoted. Okay, and then as they fall back down, that's when we see that pretty color. It's an ongoing process.
So that's happening like millions of times.
Right, exactly. And I was talking to my mom about this. Actually, that's kind of the technology behind, I want to say all, I don't know, LEDs, but all light bulbs. Like these fluorescent light bulbs, they have a gas in them. Okay, and basically you take electricity, send it through the tube, and the gas, the electrons around the gas atoms are promoted. As they fall back down, then is when they emit the light. Yep.
And they can just keep doing that?
They keep doing it. Nothing's hurt. Okay? Exactly.
So how would you get like the color change between?
That actually is right here.
Is it?
Okay, so I could have, and maybe if I can find it, I'll bring it when I come next time. But I could take this, as it kind of looks like, I could pull this out, and I could put another tube that has a different gas in there. And it would be a different color. So here's how that works. So tell me what I'm doing here, if I'm an electron. I'm absorbing energy, exactly. Okay, now the deal is that jump, okay, that jump actually is characteristic of an energy. I'm not going to do it, oh my gosh, but if I were to stack like books on here, okay, and I would be an electron around a nucleus of a different atom, and if I were to instead step up here, that would be a different jump, and that's a different energy. So that's where you get your different colors. And that's why fireworks work. That's why fireworks work. I know. You're like, really? The different colors are an indication of the different elements.
So like violet color would be like the highest energy.
Right. Violet color, she said, would be the highest energy. Yep. Oh my gosh, fireworks have really evolved over the 50 years I've been alive, so they're like fingerprints. So, okay, here you go. And we're kind of building up to this. Do you remember clear back in the beginning of, I guess it wasn't that long ago, it was just Monday, but the first slide in this chapter, okay, it was a picture of the sun's spectrum, picture of the sun's rainbow, okay? And we saw those dark lines in there. Those were actually indications of what electrons are doing in atoms around the sun's atmosphere. What? Okay, so we're kind of building up to that. Okay, so I have 3 types of spectra. Now, anytime you see the spectra, here we go. Have you ever heard like the rainbow called a spectrum? Have you ever heard of that? Okay, good. The whole Roy G. Bibb's a spectrum. Okay, so that's all we're talking about. A continuous spectrum means basically it's what you think of. The Roy, I usually go over here, Roy G. Biv, kind of like continuous, right? That's a rainbow thing. All right. Now here's one for you, an emission line spectra. Let's go back to this. When I step up, okay, am I absorbing or emitting energy? I'm absorbing energy. When I step down, am I emitting or absorbing energy?
Emitting.
Emitting, exactly. These emission line spectra are from this. Light is emitted. Okay, that's it. Light is emitted as an electron transitions from a higher energy level to its ground state.
So are we just like talking about light sources now?
Bless you. We're talking about, actually we're going to talk about gaseous clouds, like atoms within gaseous clouds that do this. But, yeah, we're getting there. Okay, there's 3. So continuous means continuous. Emission lines basically was when you guys told me I stepped down. I know. I stepped down. That would like end class real quickly, wouldn't it? Oh my gosh. The other day I was, after you guys, I was in here lecturing and my laptop ran out of juice. So that ended class too. So anyway. Okay. So absorption. Here we go. Is this absorption or emission? Absorption. Exactly. So, let's see if I put it up here. Now, when I step down, that's the emission, emitted, right? That's your emission spectra. Do you buy this, that as I step down, that's when you see that light? Okay? So actually, we're going to actually see light bands there. It's going to be like a fingerprint because it's specific for how much that jump is. Okay? If it's here, it's going to be a shorter wavelength. Okay, if it's here, it's going to be a longer wavelength because it's less of a jump. Now, some of this you have to get, and some of this are just kind of filling in a little bit. All right. So here's this. So I'm absorbing energy, right? Okay. We're actually going to see that when I do this, I'm sucking in some energy. So we're going to see these as dark lines. Okay. I'm taking in that energy. Okay. This is going to be bright lines. Okay. And as I step up, that's going to be dark lines. I'll show you hopefully what that looks like. Okay. Continuous spectrum, a light source, prism. Okay. Roy G. Biv, continuous, no breaks. And this might kind of go back to maybe what your question was, Ty. This is a case where basically when electrons, in a gas light bulb, okay, electrons basically are transitioning so that they cover all options, all wavelengths are being covered.
So they're doing that step?
Yep, so they're covering everything. Now, a good continuous source would be, as long as you don't get a magnifying glass, like Fraunhofer did, but would be from the sun. Basically, the sun is sending us kind of continuous, but we did see those.
So is it a black light? Is that only doing, are the electrons only doing one?
Yes, if you get like a light bulb that is just sending out one wavelength, then it's just, yeah, it's narrowed down. The colors, the transitions are narrowed down to that one transition. Yeah. Okay, continuous. All right, let's talk a little bit astronomy. Now this is where, picture that cloud of gas out there in outer space, okay? And picture something heating up that cloud of gas. I'll just put this whole thing up here. Oops. I think I'm missing my thing. You guys probably have that in your fingers. Oops, wrong computer. Come back. Oh, all right. All right. So picture, and it doesn't show you, let's see, atoms in a warm, so do you see the word warm? Okay. So that cloud of gas is something we want to study in outer space. Nice and warm and toasty. The important part about warm is it actually is a way that we can do this. What's that mean? Absorb, yes. We can actually excite electrons. So the important thing here is not this part, because that's just the heat, but the important part is here. What am I doing with energy when I do that? Emitting, exactly. So from that warm cloud of gas, we can get these little lines here. Okay, those are, it's not continuous anymore. It's just relative to what those hop downs are. Now you might think each element has only one line, but there's actually kind of a series depending upon kind of how the electrons are arranged. So that's a fingerprint for something. That is totally a fingerprint for something. Okay, that's emission line. The next one is, that's the second. So we had continuous, emission line spectrum, and then this is the third one, absorption line spectrum. All right. What's the difference between, I'm kind of point your attention to kind of that thing at the top there. What's the difference between that thing at the top versus the one on the previous slide?
It's been jammed upside down.
It's emitting the whole time except certain points when it's absorbed.
Yeah, it's emitting the whole time. We call that continuous. And can you see the dark bands? That is this. Okay? Just specific to what the electrons are. That's it. Okay, so that's an absorption line. That's the third type of spectrum. All right. So absorption come from this. Wait, this is my ground. Absorption come from this. Emission come from this. Okay. And that's, bless you, that's kind of what I'm wanting you to get. Now, let's see. Fingerprints. Yay. Okay. Now, I don't really throw these at you, okay? But each blue line is kind of an energy level. Not kind of, it is an energy level that the electron can be at. So you kind of see some possible transitions by the arrows. So kind of like we were up here, can you see where I'm going to focus on the 95.0 nanometers? N is nano, M is meters. Does that look like about the biggest transition? Okay. As it turns out, that's the most energetic. Okay. Over here we have smaller, okay, transitions, least energetic. Okay, you guys told me, let's see if I got this. Maybe it's coming up on the next one. It's the same slide. So, this actually, can you guys find these energies, transitions up there? They're kind of in the middle there, aren't they? Exactly. The 410.1 nanometers right here 343 right here. Okay, 486 right there. 656 right there. These guys right here. Now, I'm going to do this. This is short. And what's this? We could do like fan man up here. This is wavelengths, waves. Short wavelength, okay? That's actually, is that more energetic or less energetic? More energetic, short wavelength. So here we have short wavelength, and they're in the ultraviolet. Okay, you're not going to see that darn thing. There with those long wavelengths, that's actually an infrared. You're not going to show up. And here we have where an electron totally jumped ship from its nucleus. Okay, this is just another one of the same one. Now, how would you describe these two? These are two spectra. What's the top one? Is it absorption? How many people think it's absorption or emission? The top one. Is it absorption? Okay, very good. It is absorption. What's this other one down here? Emission. Okay. All right. So, I'm going to the last thing I want to do is to hand these out. So these act kind of like prisms.